My name is Amit Ganesh. I'm the VP of Engineering for Databases at Google. I've had an exciting journey in databases myself, starting in the mid-90s as a technical lead at Oracle in transaction processing, and then going on to develop technologies like temporal query, Exadata, and even a hardware coprocessor to help with query acceleration. I'm joined here today by Sam Idicula. Sam, please tell us about yourself.
Hi, I have also worked in database kernel for a number of years, and then went on to work on a hardware software co-design system for analytics called Rapid at Oracle. And after that, delved into machine learning, both at Oracle and later at Facebook, developing a distributed training platform. At Google, my responsibility is to technically lead the query processing and manageability areas in AlloyDB.
And have the privilege to be representing the research and development done by our awesome team here at Google. Google, as you know, has a great heritage in engineering, the world's most scalable, open, and highly resilient databases, including Spanner, Bigtable, Cloud SQL, BigQuery, and many more. We have really amazing technology across our portfolio that has been enabling developers for many, many years to build mission-critical and data-driven applications. Cloud SQL, for example, is our enterprise-ready, fully managed database for MySQL, Postgres, and SQL Server. It happens to be one of the world's large-scale managed database services. Then we have Spanner as another example. That is our transformative relational database service with unlimited global scale, strong consistency, in fact, strong global consistency, and up to 5 nines of availability. Across this portfolio, we have tens of thousands of customers around the world making use of it. So today, Sam and I wanted to share with you our next major innovation in Google's family of databases that we call AlloyDB, that is redefining the database landscape with a powerful, fully open source compatible database. We are tapping into our decades of experience at designing and managing database systems at scale, and we're bringing the very best of Google to the Postgres ecosystem. Powered by cloud-native architecture, intelligent caching, and built-in autopilot capabilities, AlloyDB offers superior performance, availability, security, and scale for the most demanding enterprise workloads. With full compatibility with PostgreSQL, customers have true portability and benefit from the entire Postgres ecosystem. We started on the journey by taking PostgreSQL and adding the elements we know best, a cloud-native architecture that uses Google's unique disaggregation technology to scale both compute and scale storage, and also scale each of them independently. Our awesome engineering team combines expertise in databases from within Google across the industry, along with Google's DNA in AI and ML to make every aspect of running databases easier. AlloyDB provides industry-leading performance and availability, so it can handle any commercial workload you throw at it. It has 4 nines of availability, inclusive of maintenance. And in fact, if you look at reads, they have 0 downtime during planned maintenance operations. It is the fastest PostgreSQL database service. It is 4 times faster for transactional workloads than standard Postgres. This means that you can scale your applications well beyond what is possible, and which means you get better performance with fewer resources and smaller database instances. And best of all, query performance scales linearly as you add more compute resources to your system. In addition to building the most powerful Postgres database service for mission-critical workloads, we wanted to enable developers to build the next generation of applications. So to help with that, AlloyDB features an analytic engine based on columnar technology that runs queries 100 times faster, allowing applications to make decisions using analytics in real time. Additionally, with AlloyDB, we are also bringing Google's strength in AI/ML to database transactions, allowing customers to do machine learning-based inferencing in real time within their applications. To make all of this possible, Google developed a unique architecture that I will ask Sam now to walk us through.
Thanks, Amit. Let's now delve into each of the areas that Amit talked about and see how AlloyDB's architecture enables those capabilities. Starting with OLTP and query processing for transactional workloads, there are several elements of our architecture that enable high performance, availability, and scale for such workloads. We start with an optimized transaction engine that's fully compatible with Postgres, and then we combine it with an ultra-fast tiered cache that allows us to access the data needed by users' transactions with very low latency. Our disaggregation of compute from storage not only enables us to horizontally scale data volume and write throughput, it also offloads the database nodes from tasks like checkpointing and block writes, and that enables the database nodes to fully focus on transaction processing and queries, and that improves the performance of the workload. We go one step further in disaggregation to separate log processing and block versioning that are done by our intelligent storage engine from the actual data persistence that's handled by our distributed file system. Each layer in this architecture then is specialized for a class of tasks, and that enables each of those layers to be optimized for that class and to be scaled independently of the other layers. What that means is that depending on the load in each layer, we can scale up or down that layer and eliminate hotspots and bottlenecks, and that allows us to provide predictable performance. As you can imagine, it's very challenging to build distributed storage systems spanning multiple data centers, especially when data grows and needs to be resharded and so on. This is very hard to handle in a reliable and load balanced way. In this architecture, we avoid reinventing the wheel and solving all those problems all over again by reusing Google's proven Colossus system that gives us highly durable cross-zone replicated persistence. Now, all of these layers are also interconnected using Google's high-speed network, and that contributes to our performance as well. Our distributed storage is also shared across all the replicas of a database. What that means is that it allows us to provide very fast recovery from any failure, and also allows us to provision read replicas very fast. So when higher throughput for queries is needed by an application, users can quickly spin up read replicas to meet that demand. Read replicas can also be organized into pools of nodes, and user connections can be served by any node in a pool. So if we need to do maintenance on a particular node, or a node goes down for any reason, users' query workloads are not affected. So there's near zero downtime for read-only workloads, in addition to the linear scaling of query throughput that the read replicas and their fast provisioning provides. We also built an analytics engine and integrated that directly into the database so that users can process analytics in the same database that they use for OLTP. There are several advantages to this architecture. One is the fact that we provide real-time analytics with zero impact on OLTP throughput. There's also no complex ETL process for developers to develop and manage. There's no separate analytics system to configure and manage either. We've also built ML-based intelligence and integrated that into the database in multiple ways, both to automate the management of buffer cache and database processes like Postgres Vacuum, but also to enable users to directly get further insights and extract value from their own data. And I'll talk about some of these aspects more as we go along. As Amit said, our columnar analytic engine can provide very high performance for analytic queries. And here we are leveraging Google's expertise in analytics and reusing the columnar technology that underpins systems like BigQuery and F1. We automatically analyze workloads, looking at query patterns and data, and we determine what is best to be organized into a columnar format in memory and load those data items automatically into memory and organize them in the columnar form. Along with that, we also learn metadata about this data, and that helps us to prune data to be scanned when there are filters to be executed. We use SIMD instructions to provide high performance execution for columnar operations. And after combining the result of several filters, we are able to perform columnar aggregation on the data without having to materialize the results after filtering. We also optimize joins using techniques like Bloom filters to provide significant acceleration for queries that involve joins. And all of this is done in a way that's fully Postgres compatible. So Amit mentioned the fact that our analytic engine can provide up to 100 times faster query performance. So here's a look at a few different queries to provide more insight into how we accelerate different query patterns. So the first query is a simple aggregation with selective filters, and we accelerate that query by 117 times. The second query is a grouped aggregation with less selective filters, and we accelerate even that query by 19 times. The third query has a join with the same set of less selective filters, and using our Bloom filter-based acceleration on the join predicate, which is somewhat selective here, we provide an 8x acceleration for this query. The fourth query operates on the largest table and doesn't have a selective join, and even for such a query, we provide acceleration of 160%. So as you can see, we accelerate a wide variety of query patterns here, and over a wide basket of queries, we expect significant overall performance improvements. All this is happening in a fully transactionally consistent manner, with the optimizer automatically choosing the columnar engine where it's useful. So what that means is that indexes that users may have created previously to accelerate analytic queries could be dropped now, and that can further improve OLTP performance. So with our columnar engine, we're enabling users to get analytic insights directly on their OLTP databases. Now, we're also helping developers to integrate intelligent insights into their applications in another way. As you know, Google has deep expertise in AI, and we've provided a way for users to bring the power of ML models directly into their SQL-based applications. Let me explain how we do this. We've added a new SQL function, ML Predict, that allows users to invoke predictions on models deployed on Vertex AI from within their SQL queries and transactions. Now, in this example, we're looking at the processing of a payment transaction. And as part of the processing, the application makes a call using ML Predict to a fraud detection model that's deployed in Vertex AI, gets the result of that prediction, and integrates that with the processing of the transaction by inserting that data also into the database. This allows applications that access the data later to also get the result of the fraud prediction. Now, this technology can also be used flexibly in queries, and that allows use cases like sentiment analysis as well. Now, at this point, I will hand it back to Amit.
Thank you very much, Sam. As you can see, AlloyDB really reimagines how operational databases are architected, combining industry-leading availability, industry-leading performance, along with real-time analytics that is up to 100 times faster, and then machine learning to help developers build those next generation of innovative applications. So that's all we had to share with you today for AlloyDB. But if you have any further questions or would like to connect with us, feel free to reach out to either me or Sam. Thank you.